there are no questions at this forum, but the speakers will be outside, and the talks are so interesting, there is no way you wouldn't be back down for questions. The next topic is simulation governance, an idea whose time has come, by Barna Szabó, who is the president of ESTR and the father of P finite element methods. Please welcome Mr.
Thank you very much for the introduction, and thank you for the invitation. I really enjoyed being here. I realize that we're running late, and I will try to get to the main points as quickly as possible. I will speak about simulation governance, and in particular, I will address what is simulation governance, why is it important, what is simulation, what is numerical simulation, and the big question of why finite element modeling is not numerical simulation. This may be surprising to some of you. And then what can be done now. What is simulation governance? I define it to be as command and control over all aspects of numerical simulation. There are two branches of simulation governance, which are interrelated but nevertheless distinct. One is the creation of design rules. This is the responsibility of the authorities who establish rules by which we design things. And the other one is the application of design rules, which involves the design itself and certification. The objective of simulation governance is to ensure and enhance the reliability of predictions based on numerical simulation. Why is it important? Well, as we heard before, there are very strong economic incentives to reduce reliance on physical testing and increase reliance on numerical simulation. I think this is obvious. This is possible only if the reliability of predictions based on numerical simulation is first established. Simulation governance provides the ground rules for sound simulation practices. So then let's ask, what is simulation? By definition, simulation is the imitative representation of the function of one system or process by means of the functioning of another. So we will be concerned with the simulation of some physical reality by mathematical means. So we have the physical reality, and there's a transformation. We have data that describes that physical reality. We have intelligence, information, past experience, expert knowledge that we apply. And what we would like to do is to predict the performance of the reality under some changed circumstances. And this prediction is represented by F in this box in the middle. So the goal is to make predictions. So the transformation of data together with the background information I and the intelligence that we apply to it leads to a formulation of a mathematical problem. Please note, it is the mathematical problem. The goal to formulate that problem is what is an essential part of simulation. The solution of this problem is used for predicting the data of interest F. So then let's ask, what is physical reality? My favorite statement on this subject is coming from Wolfgang Pauli, whose picture you see here. He's a Nobel Prize winner for physics in 1945. He's an Austrian physicist. He said, the layman always means when he says reality that he's speaking of something self-evidently known. Whereas to me it seems the most important and exceedingly difficult task of our time is to work on the construction of a new idea of reality. So this is distinguishing between reality and our idea of reality. And this is fundamental for us to understand because this transformation I spoke about is conditioned on the analyst's idea of physical reality. So it has a subjective element which may change over time, and it does change over time. So I really never understood what the term physics-based model means, because the physics-based model is not something that even Wolfgang Pauli would have been able to figure out. Then what is numerical simulation? Well, the problem is that the physical reality, having constructed a mathematical model of our understanding or our idea of physical reality, leads to a system of equations or problems, typically in a variational form, that cannot be solved except by numerical means. So we really never see f, we only see the numerical image of f and base our prediction on this numerical image. So the numerical image of f is an approximation to f. To ensure the reliability of prediction, the task is to compute this numerical image and show that the error, the difference between the solution of the mathematical problem and our numerical approximation of it, is within a specific tolerance. That is represented by the equation here. So then what is finite element modeling? Well, my understanding is finite element modeling starts also with a physical reality and the intent to simulate that physical reality. However, the analyst, instead of thinking through what the mathematical problem is that will represent his idea of physical reality, entrust this task to the developer of software tools. So they go to an element library and they piece together elements when the nodes permit them to piece those elements together, and they believe that this represents a realistic mathematical problem of something. So there is no concept of the solution of a mathematical problem because it is only a numerical system that they have created. So they only see the numerical solution, a numerical image of something that is not clearly defined. So in the definition of the model and approximation, this is the original sin of finite element method, which occurred in the 1960s when the mathematical model and the approximation were mixed in these element libraries. A clear definition of the mathematical problem is therefore missing, and in fact, the data of interest may not even exist. And I will show you an example, the very simple example that this happens a lot. So the most important technical requirement of numerical simulation, that is estimation of errors of approximation, cannot be satisfied because if you don't have an idea of what the solution of the mathematical model is, then you cannot calculate the error, you only see the numerical image. So this is why I say finite element modeling is not numerical simulation. Let me give you a very simple example. Here is a log, and it is loaded, as you see, by a load F. And what we would like to do is to find the average displacement of the loaded hole for a fixed value of F and the angle alpha when the points, the circles represented from 1 to 6, are somehow constrained, representing a fastener constraint on this. So what a finite element modeler would do would make a mesh, and thinking that, well, the size of the fasteners is small, let's just fix those nodes where the centers of the fasteners are and apply the load and solve this numerical problem. This numerical problem will have a solution, obviously. And so when they compute the von Mises stress at polynomial degree 1, they see this. And then they solve it for polynomial degree 2, they will see that. When they see polynomial degree 3, then they notice, aha, there are some strange things occurring at one of the fasteners and maybe another 2 as well. And you go to p=4, you see those strange things pop up. Why? Well, because the input data that was used, namely a point constraint, is not allowed in the mathematical formulation of elasticity. This is not a legal input data. It doesn't lead to a solution. So then if you continue to p=5, you see that these spikes keep on going, and you get the idea if we kept increasing the polynomial degree, this would go to infinity and has no meaning. On the other hand, what is maybe disturbing, that many analysts believe that because they observe equilibrium in the applied load and the constraints, and however these depend on the polynomial degree. So the nodal forces will satisfy equilibrium on every element. Many analysts mistakenly believe that equilibrium of nodal forces is an indication of solution quality. This is satisfied independently of the finite element solution. So instead of solving the numerical problem and finding the finite element solution, you just went to a random number generator and got any set of numbers and plugged it into, and the nodal forces would be in equilibrium. So therefore, this is absolutely nothing to do with the quality of the finite element solution, and this is something that is a pervasive conceptual error in the finite element analysis community. Well, what would happen in the data of interest? I said F in this case was the average displacement of the loaded hole when the force was applied. As I increase the polynomial degree by increasing from 1 to 5, as you see, the average component of the component of the average displacement denoted by ux here is just going to go diverge, and it goes to infinity. So in fact, the reporting any kind of a numerical result will be has an error which is infinitely large, which is a complete nonsense because of the violation of the underlying problem of elasticity. So what is the explanation that we found things in equilibrium, but you saw that this thing is diverging? The equilibrium occurs because there is a crude modeling error, which is meaning that inadmissible constraints were used. But it appears reasonable because the error of approximation is also very large. So these two errors nearly cancel one another, yielding a seemingly reasonable results. And in other words, if you really look at those fastener forces, if you didn't carry the mesh fine enough or the polynomial degree high enough, then the answer is believable, but nevertheless it's completely wrong. So any value can be obtained for the joint stiffness just by changing the discretization. The creation of design rules is too large of a subject for me to go into it. I just let you know, I just wanted to mention that this is where verification, validation, and uncertainty quantification comes in play. And one of the big problems in computational solid mechanics today is to figure out what are the design criteria, what are the design rules for composite joints, such as this pi joint here. The application of design rule is simply the designer is asked to verify, number one, that the numerical solution is not far from the exact solution, and second, that the numerical solution will be less than an allowable value, but elevated by the potential error in the approximation. Therefore, any tolerance, any error in the numerical solution, if you honestly take it into account, will penalize the design by simply increasing the value on the right-hand side. Here is an example of solution verification. A joint is indicated here, which is loaded by moments and shear forces. And this is a typical indication. I didn't show it on the other cuts of the pipe. And if you want to study the example of the effects of the chamfer, you will see that we can find on the chamfer at the intersection at A is going to be rounded, whereas the intersection at B is remaining sharp, and you see the difference. But the key point is what you see would be that as the number of degrees of freedom increase, that the data converge to a limit. And so this is the feedback that I need to know that the solution is not substantially mesh independent or polynomial degree independent, and therefore cannot be too far from the exact solution of F. Without this, it would be practically impossible to estimate the error of approximation. So what can we do now? Well, I'm speaking to managers now primarily, but we all should be concerned about what the technical requirements of simulation governance are. We need to review existing simulation practices, replace the practice of finite element modeling with numerical simulation. I think managers should state that you are willing to pay for computed information only if its reliability is established. Why would you pay for something that is unreliable? Insist on verification and introduce standard processes for recurrent engineering analysis tasks. This is possible to do, and I will show you some examples. I would recommend a reading on simulation governance. I published this paper 2 years ago, and would like to draw your attention to it because a lot of things that there is no time to discuss are explained in detail at that point. I hope that you don't mind that I'm promoting my own paper here. What is the standardization? There is a CAE handbook which we created that allows standard parts to be created by expert analysts. These expert analysts know what the subject is. They prepare parametric models that are then made available subject to the requirements of solution verification to analysts or to designers who need that information but do not want to bother with finite element analysis or don't know how to bother with finite element analysis. And the documentation of each entry is done very carefully with an expert analyst who has to meet certain standards and qualification. Essentially, the potential here is if we compare it to the traditional handbook of Rourke and Peterson, which was an assembly of expert design solutions, I claim that with today's computational power, an experienced and knowledgeable analyst will have the power to solve problems in a systematic, parametric way that Timoshenko could not even dream about, because we have this tool and we have all the procedures established, documented, and the knowledge base exists for that. Here is another view of the CAE handbook, how the solution looks once it is performed. And the user interface is very friendly, very intuitive, much the same way as one would expect in today's industrial environment. It also serves to preserve corporate know-how and knowledge and to archive it and to make it available across the large enterprise. So in summary, the CAE handbook is in analysts create and verify, establish the technical requirements, create handbook entries, produce documentation, perform code verification. The designers utilize by selecting the appropriate parameters, obtaining the verified solution in one click, and interpret the results. Of course, this is possible only if you have a clearly defined problem. We worked with the American aerospace sector to create some so-called smart applications of recurring analysis tasks. And one of the most difficult part was to collect the technical requirements and make sure that everybody could sign off on it before we started to write the code. So in summary, management is responsible for the command and control on the overall aspects of the numerical simulation. Most managers relegate this to junior engineers or less senior engineers, and this is not a good idea, because management is ultimately responsible for the adoption of the best available simulation practices, which include solution verification, data verification, model validation, revision of mathematical models in the light of new information collected from physical experiments, and the observation of unexpected events. The goal is, of course, to ensure and enhance the reliability of predictions based on numerical simulation. Let me close with an opinion expressed. I believe that if Filippo Brunelleschi relied on finite element modeling, he could not have built the dome of the Basilica di Santa Maria del Fiore. Thank you very much.